Quadratic introduction. We will work on this together. So, my job as a math teacher is to help you make connections and see patterns, and not so much the whole right answer thing. Right? I give you the answers. It's the connections I want you to understand. So we're going to work on this worksheet today, which is all about connections. So if you take a look at the first row of dots, let's make a table of values. Wow, that was cool. So if this is my X list and my Y list, what do we start with for X's? What numbers should we put in the X columns? You could start with 0 or you could start with 1. Does it matter? No. Not really. It will make some changes later on, but we'll deal with that. So 1. How about we start with 1? Yes. Do as I'm doing. Follow me. Okay. These people watching the video are wondering what that big gap of nothing was. So, how many dots are there in the first box? 5. And the second? 8. And the third? 11. And the fourth? 14. Okay, do you see a pattern? It goes up by 3 every time. If I create another column over here, what do I call that column? First, the difference. So this is the first difference. And the differences are calculated by taking any value and subtracting the value above it. And essentially, we have a whole bunch of plus 3s. Now, if the first differences are all the same, what type of function are we looking at? A linear function. So in this linear function, we're going up by 3 every time, and linear functions can be equated using mx plus b. What is the equation for this function? Right, that's the generic, mx plus b. What's the specific equation? Nice try. You can't just change the variables and call it. What are we changing by? 3x. 3x plus what? Well, it's got to match the 5. When you plug in 1, you have to get 5. When you plug in 2, you have to get 8. 3x, 3 times the number we're looking at, plus 2. So our first differences are 3. We're going up by 3. That's where 3x came from. And 3 times 1 is only 3, but there are 5 dots. And 2 times 3 is only 6, and there are 8 dots. That's where the 2 came from. Okay? Now, it's my job to help you understand how all of this connects. And it connects way more than you think it does. So, do you see plus 3 in every single picture? Okay, think about it for a second. Don't tell me where it is. Look at the pictures. Do you see plus 3? And I'm willing to bet that not everybody sees it the same way. So look at picture 1 and then picture 2. Do you see plus 3? Look at 2 and then 3. Do you see plus 3? Okay, where do you see the plus 3? Yes. Where? So you see this. And that happens every time. Oops. Except when I do it. Okay, so if you look carefully, this picture is right here with 3 dots on the side. Hang on, we'll get to yours. And then this picture is right here with 3 dots on the side. Right? And then this picture is right here with 3 dots on the side, but not everybody sees it that way. Okay, I told him we'll let you go for it. So you could say these dots are new. We put a new column in the middle and spread the edges apart. And then these dots are new, and these dots are new. Who's right? Both. Right? It's just plus 3. Whether you add them in the middle or you add them on the edge, or even you could add on one edge and then the other edge and then the other edge, or it's all the same thing. It's all the same pattern. Okay? Well, we should be able to see, this is a little bit harder, but it's still doable, 3x plus 2. What does x mean in this case? No, x is not dots. What does the left column represent? What do these numbers mean? Which box we're talking about? So this is box 1, 2, 3, and 4. Those are the inputs. Those are the domain. Okay? 3x plus 2. Do you see 3x plus 2 in the boxes? Because we should be able to. 3x plus 2. X is the number of the box. So in box 1, you should see a single x. In box 2, you should see 2 x's. In box 3, you should see 3 x's. And so on. Does anybody see plus 2 in any of the boxes? Okay, we're not looking for the letter X. That doesn't work. Okay. This is sort of the key. We're looking for a 2 in every box. We're also looking for some sort of 3 that changes. The 3's get bigger. In the first box, there's going to be 1 3. In the second box, there are going to be 2 3's. In the third box, there are going to be 3 3's. Where are they? So here are the 2's, right? That's the plus 2. And then we have 1, 3. That's where x comes in. We have 1, 3. What about the next one? Does the pattern follow? That's my 2. What about the 3's? 2 3's. And the next one will have 3 3's plus 2. And the next one will have 4 3's plus 2. Okay? Now, at the beginning I asked, does it matter what we label the boxes? Somebody wanted to start with 0. Do you want to close that door? Sorry, it's distracting some of you. What if we started with a number other than 1? And you can start with whatever you want. And the pattern and the y column is not going to change, but your equation is going to change a little bit. So if I went through and started, say, at 0, instead 0, 1, 2, and 3, so this would be 0, 1, 2, and 3, that changes my equation. It's still y equals 3x plus something, but it's no longer 2. What would it be? If I plug in 0, 3 times 0 plus something has to equal 5. So by changing my x values, I did alter the equation a little bit. The pattern is still the same, but the number I plug in is a little bit different. Can you see 3x plus 5? Well, it's a little bit harder to see, but I'll show it to you. So we have to have 5 boxes to begin with, and then we start adding however many columns of 3 we need. In box 0, there are no columns of 3. So these are my 5 dots. Right? No columns of 3. Here are my 5 dots with 1 column of 3. Right? Because box 1 has to have 1 column of 3. And then here are my 5 dots with 2 columns of 3. Well, it's different. It's box 0, so we need to find no columns. So that plus 2 became plus 5 because that first column of 3 is now part of our plus 5. Okay? Oh, don't worry. Don't worry. Rest assured it's going to get worse. Okay. Next set of dots. Yep. Okay. What should we start this one with? Let's start at 0, just for fun. So 0, 1, 2, 3. Okay, so this is box 0, box 1, box 2, box 3, box 4. And it really doesn't matter where you start. I just picked 0 because it was fun. How many dots are there in box 0? And the next one? 2, 4, 8, 16. Okay, so this is x, this is y. Let's calculate our first differences. What do I get for my differences? Plus 1, plus 2, plus 4, plus 8. Is this linear? No. So let's see if it's quadratic. Go to the next differences. Plus 1, plus 2, plus 4. Is anybody going to talk me out of this? Sorry. So we looked at our y's. What do you need to add to each y to get the next y? Itself, basically, right? How many differences will I need to calculate before I end up with the same number over and over? Well, it's never going to happen. My y's are 1, 2, 4, 8, 16. My first differences are 1, 2, 4, 8, 16, 32. My second differences are 1, 2. Anybody want to take a guess what my 49th difference is going to be? 1, 2, 4, 8. How far do you have to go before those differences become the same number over and over? It's never going to happen. So this is not linear. It's not an x squared. It's not an x to the third or x to the fourth. Okay? It's something else. It's actually what we call exponential. Okay? Do you notice a pattern in the y's? Obviously, this didn't work. What pattern do you see? Multiply by 2. So the pattern is times by 2. Okay? How many 2's do you need? How many times by 2's do you need? Well, it depends on what box you're in. In box 1, how many times, box 0, how many times do we multiply by 2? In box 0, none. How many times did I multiply by 2 in box 1? Once. And in box 5? 5 times. So the equation is really easy. It's just y equals 2 to the x. 2 times itself, x times. And in box 0, 2 to the 0 is, if you never multiply 2 by itself, you get the number, no, box 0 is 1, which is weird. 2, how many multiplies by 2 had happened in box 0? None. So 2 raised to the 0 represents how many dots? 1 dot. Okay? So can we see 2 to the x in the boxes? I should be able to see the equation in the boxes, right? Well, multiplying by 2 just means double. So if you look at box 1 and then box 2, do you see a double? Yeah, it's actually pretty easy. This is a new dot. It's a double. What about between 2 and 3? Do you see a double? Where is it? Those are new. They're an exact duplicate of what's above them. Between the next 2 boxes, do you see a double? So right here. And then right here. What would the next box look like? Would it be square or rectangular? It would look like this, and it would have 2 copies of 16. What would the next box look like? It would be square with that many 16s. What would the next one look like? It would be a rectangle with 2 copies of 4 16s. Okay. Well, we hit 64. The next one would be 128. Yeah. Okay, so that's what an exponential pattern looks like. Turn the page. This one's kind of strange. Let's start with 1 in this case. And actually, I'm picking a specific number to fit my needs. Any number would work, but 1 is easier in this case. So 1, 2, 3, 4, 5. Okay. So my y values, how many are there? 5, and then, not 7, 12, and then 32, and no. 40, 45 is the number. Okay. Is there an easier way to calculate that than to just add them all up, count them up? How did you get 45? Who got it? How'd you do that? Okay, so you did 4 by 8. Oh, no, you found the pattern. Oh, okay. Well, that's not what I was looking for, but that works too. Let's just look at that last box, box 5, or it's actually box 4, right? Sorry. 1. How did I mess that up? Oh, it's not there. Sorry. I see why I'm confused. There is no box 5. So look at box 4, 32. How would you calculate the 32 in a fast way? Okay, if all you had was 32, if all you had was box 4, how would you wouldn't count them up, right? How would you do it? Okay, so what are the numbers? What would you calculate? And there's more than one way to do this, so I want a couple different versions. So I want to calculate how many dots are in here fast. How would you do that? Okay? Okay, so he looked at that and said, all right, we have 4 on each side. Those taken together are exactly the same size as the box on the inside, right? They're the same size as this. Is that true for all the other boxes? Are the dots on the outside taken together the same? And that's okay. I mean, it's not a big deal, but it works for that one. Does it work for 3? Does it work for 2? Yeah, does it work for 1? Okay, so it works for all of them but 1. So that's good news. Yes.
I would do, 4, 4, 6, 6 times 4 is 24, and you can see that there's a lower row of 4, 4 times 2 is 8.
So you looked at it and you said,
There's 4, 4,
this, right? So we have a box that's 4 by 6 plus an additional 8. So 4 times 6 plus 8. Okay, that works. Anybody see another way? Okay. So the whole thing is 6 times 6 minus the original, the 4 corners. Okay, all of these work, and they're actually all important. So let's look for patterns. First difference, plus 7 plus 9 plus 11 And then this one, which we calculated, is going to be plus 13. Is this linear? No. But the first differences go up by 2. So we end up with plus 2, plus 2, plus 2. If the second differences are constant, what does that mean about the equation? Not linear. Quadratic, which means it's an x squared. I understood what you meant. So we have a quadratic equation. It's some version of x squared. Now, sometimes quadratic equations are really hard to see, but I picked one that's pretty easy. Whenever you hear quadratic, there have to be squares involved. Now, x represents box numbers. So this is box 1, box 2, box 3, and box 4. And we're looking for squares. So let's use the dots to figure out what the equation is. Do you see any squares that correspond to the number of the box itself? So what we want to do is link box 1 to a square that has something to do with the number 1. We want to link box 2 to a square that has something to do with the number 2, and so on. Do you see what I'm saying? So a square, what is a square? Has 4 sides and they're all equal. So a square has length and width that are the same, right? Well, the length of these squares has to be the same as the number on the box. So do you see x squared in box 1? The middle. So is this a square? Not what I drew, but that dot. Good job. Okay, what about, so he mentioned that. Is that a square? I drew a square that time. Maybe this will make you feel better. There you go. In box 2, is there a 2 by 2 square? In box 3, is there a 3 by 3 squared? So part of the equation, every box has an x squared in it. Is that all that's there? So this has a 1 by 1 square, and this has a 2 by 2 square, and this one has a 3 by 3 square, and that one has a 4 by 4 square. But does that describe all of the dots? No. How many more dots are there?
1, 2, 3, 4. On each side.
It depends on the box, right? Well, it's 16 on some of them, but not on all of them. How does the number of dots that we haven't counted compare to the size of the box total? So how many extra dots are there? And the answer is it depends on the box. So we need to link the box number to the number of extra dots. No. That was a bad idea. Okay, so here we have a 1 by 1. How many extra dots do we have? 4. Here we have a 2 by 2. How many extra dots are there? 8. Here we have a 3 by 3. How many extra dots are there? 12. Here we have a 4 by 4. How many extra dots are there? It's 4 times the box number. You see that in the picture, right? This matches the box number. This matches the box number. This matches the box number. That matches the box number. How many copies of that matched box number are there in each picture? 4 of them. There's one on each side of our square. So what you're telling me, without realizing it, is this is the equation. To find out how many squares are in any box, you take the number on the box and you square it. That represents all the dots in the center. And then around that box are 4 sets of dots, and each set of dots is equal to the number on the box. So x squared plus 4x. That's the equation. Okay? Is that the only way to do it? Of course not. We looked at it a different way. We'll call it the Eli-Beagley method. Eli, remind us, how did you add up that box? So Eli said, if we had dots there, then this is simply 6 times 6 minus 4, right? Okay, well, it's a little bit tricky because the box number is not 6, it's 4. Okay, so we could calculate this as 6 squared minus 4. What would this one be? So that's 5 squared minus 4, and this one? Yeah. This is 4 squared minus 4, and this one would be 3 squared minus 4. This would be a 3 by 3 minus the 4 corners. Okay, so if my box was 10 squared minus 4, which box number am I looking at? 8 or 9? If I have 10 squared minus 4, what box does that represent? 8. Why 8? So you're telling me that the square, the big square we're looking at, is 2 bigger than whatever's on the box. Everybody agree? So this number plus 2 is that. This number plus 2 is that. This number plus 2, and this number plus 2. So what if my box number is x? What's the pattern? If my box number was 6, how would I calculate the number of dots? Keep going. 6. We just said it. 6 plus 2 extra dots. And then what? Squared minus 4. So the box 6 is going to be 8 squared minus 4. What's box 25 going to be? 25 plus 2, so 27 squared plus 4. That's how many are in box 25. So for any box x, it's x. What do we do to the number on the box? Add 2. And then we square it, and then we, subtract 4. But wait a minute. Are those the same equation? Because they tell the same information. They don't look the same to me. Well, let me show you. Our first equation was x squared minus 4x. Our second one is x plus 2 squared minus 4. But x plus 2 squared is really x plus 2 times x plus 2. And then we subtract 4. And we'll talk more about this later. But multiplying binomials, we multiply that and get x squared. Then we multiply that and we get 2x. And that gives me 2x. And this gives me plus 4. But that's minus 4. And what do you notice? 4 and negative 4 cancel. And that is exactly the same thing as that. So all of this mathematics is connected in ways you don't understand. My job is to help you understand the connections. And you'll forget the connections. You're not going to use this in your life, but learning how to make those connections is valuable. That's why you're in here. You're learning how to problem solve and how to make these connections, and that skill will stay with you, even if you don't use it in mathematics further on. You know, you look at your kids and you'll say, this caused that, and that caused that, and that causes me to want to take a nap. And then you'll do it, and you'll be happy. Okay, that assignment is done. You can hand it in.